Good morning, everybody. I think it's time. Welcome back. So before we get going with our class today, I just want to say first of all, there's no homework this week because we only had one day of new material last week, so we're just going to roll that into the next homework if that's all right with everybody. And I graded the tests. I hope that you have had a chance to check it out. I know some people went. You can go to Gradescope and see your grade. You can also see my comments. I don't know if you have all been looking at my comments on the homeworks from week to week, but you can see my comments on your assignments, problem to problem. Is anybody there? I hope you are.
Yeah, I look at the comments.
Okay, great. I meant, is anyone in the Zoom now? Everyone has their cameras turned off, which is alright, but yes, you can see the comments. If you can't figure out how to do that, let me know, and I would be happy to help you see my comments. Or if you just have other questions or whatever, I would be happy to talk about the test. Some people did great. I think the highest grade was 98 or something, so excellent job. And there were several people who did really well, and some people did not so well. Looking over the grades overall for the semester, nobody is really screwed at this point. So if you did not do so well, then I hope that this can inspire you to do better in the future. But nobody is in a really bad position right now in terms of the grades. If you would like to know what your overall grade so far is, let me know, and I would be happy to tell you what I got for you in the grade books. All right. I thought so. I don't think we need to go over in detail the test, question by question. But I would like to go over one of them, which you can see on my screen here, is number 2, because almost nobody got full credit on this one. A lot of people did pretty well, but I think only one person got it all right. So let's just talk. I just want to go through this one, and then, like I said, if you would like to talk about other ones, I'd be happy to sit down with any of you and go over the test in more detail. All right, so let's talk about this one. This was a volume of revolutions problem. These are difficult, as you know. It says the volume obtained by revolving the area bounded by y equal x squared plus 1. Okay, so you got to draw the picture correctly first of all. X squared plus 1 is the parabola but moved up by 1, so this is the function x squared plus 1. And then we want to revolve this bounded by that, y equals 1, x equals 1. So y equals 1 is this line, and then x equal 1 is this, this line here. So the area that I'm talking about is this kind of triangular sort of shape here. And then we need to rotate this around the x-axis, it says. So we're going to just sort of spin it around like that. The x-axis, right? This is the shape that we're talking about. And you got to do the washers thing for this. I mean, some people tried to do this with the shells. The shells is not really appropriate. It is possible to do with the shells, but you'd have to rewrite the equation as y's in terms of x, because the shells, if you wanted to do the shells, which you shouldn't, they would look like this, right? They're going, is that too small? The shells, if you wanted to, would look like this. Here's one shell. The height of the shells would be given by x values rather than y values. So you'd have to change around the whole scenario, do the integral in terms of y if you wanted to do the shells, which is not worth the trouble because the washers is easier. So don't do the shells in this example. Do the washers. The washers means I'm going to be slicing the picture up sort of this way. and each time I measure the inner radius and the outer radius, where the rotation is around this axis, right? The x-axis here is the axis of rotation. So the inner radius each time is this distance from here to here. That's 1. So the inner radius, the r inner, is just 1, and the outer radius, depending on the x values, is given by this height all the way from the x-axis up to the curve. That is simply the equation of the curve, x squared plus 1. All right. Sometimes you have to modify that if there's like extra distance to the axis, but this is just the distance from the curve to the x-axis, which is whatever the equation of the curve is. All right. Great. So now we can do the integral, I think. So you got to go the integral. The integration boundaries would be 0 and 1 because that's where the x values go, and then it's pi times the outer radius minus the inner radius. So x squared plus 1 squared. That's the outer radius minus 1 squared is the inner radius. And then this is the integral that we have to do. And to do this integral, you should actually square out that thing on the inside. X squared plus 1, the whole thing squared, becomes x to the 4 plus 2x squared plus 1. That's the doing like the FOIL thing with that. And then I have minus 1. This 1 is right there. So the 1's will cancel and you get some simple thing. Like that, right? Do the integral, you get 1/5 x to the 5 plus 2/3 x to the 3. Plug in 0 and 1. You plug in the 1, you get pi times 1/5 plus 2/3. Whoa. And you plug in the 0, you get 0. So that's the answer here. All right, I just wanted to go through that one, like I said, because not a lot of people got this right. Are there any questions about that one or about other ones? I mean, we can go through any other ones that you would like to. This is the only one that I wanted to do.
Could you do question 6?
Yeah, sure. Let me. So I got to get out of my full screen Zoom here to see my. I don't have the test on paper. Number 6. I'm getting there. Okay, number 6. Simplify these into a single logarithm. That's the one?
Yep.
Alright. I'm just copying this problem down onto my screen. Okay, so it's like that, right? Simplify this into a single logarithm. The rules that we're using are the ones about the log of two things added is the product and the log of two things subtracted is the quotient. So if I were to combine just the first two together, it would say, actually first, before doing the quotients and the products, whatever, let's put the exponents inside each log. So this, first of all, becomes log of x to the 4 minus ln x plus 1 to the 8, and then the last one you can't do anything like that. And then now we can combine them with the minuses and the pluses. So the first one is a minus, which means these two combine to be x to the 4 over x plus 1 to the 8, right? And then I have plus this other one. This is the rule about, you know, what I just did was log of, well, I'm using it for ln. It's true of any log, so ln of a minus ln of b equals ln of a divided by b, right? And then the plus gives me multiplication inside the log, so I get log of x to the 4 over x plus 1 to the 8 times x minus 1, right? Or if you like, I mean, you can kind of just looking from the very beginning, or from here at least, you can just say that this is going to make a big product where everything with a plus is in a numerator and everything with a minus is in a denominator. So that would you know, from that point of view, you could just jump from there to something like x to the 4, x minus 1 over x plus 8. No, x plus 1 to the 8. All right. A lot of people wanted to put the x minus 1 in the denominator also, but it shouldn't be because it's a plus right there. If there had been parentheses like this, then you would interpret both of those as being minuses because you would distribute the minus, and then they would both go in the denominator. But there were no parentheses like that, so it shouldn't be like that. It should be like this as written. The two positive things go in the numerator. Does that seem all right? Any question about that?
Yeah, that's I did what you were saying.
Okay, with the denominator, yeah, a lot of people do that. I'm not sure exactly why, but it's all right. I'm not here to tell you how to live your life. I just take off points. All right. All right, great. I had one more announcement. So I said at the beginning, there's no homework this week. That means we're also going to have no quiz this week because the quiz is always just based on the homework. And my second announcement is, in the town of Fairfield, all of the children are starting regular school hours next week, which means there is no longer any reason for me to stay home every Tuesday. And so I will be coming to class in person on Tuesdays from now on. We've always been doing Tuesday by Zoom, but so today is the last of the Tuesdays by Zoom. Of course, you know, you can always tune in by Zoom like you have been, even when I'm in the classroom, but I'm gonna do it in person every Tuesday from now on. All right. Great. Anybody have any more, you know, questions about anything before we get going? Resume the class. All right, great. Let's resume the class then. So we are going to resume our discussion of the indeterminate forms and L'Hopital's rule. Right? We started talking about this, I guess, a week ago. El Hospital. All right. L'Hopital's rule is a cute trick for finding the limit of something where when you try to plug the numbers in, you get 0 over 0. That's called an indeterminate form. So the classic scenario where you would use L'Hopital's rule, we did an example like this last time. How about the limit as x goes to 1 of x squared plus 2x minus 3 over x squared minus 3x plus 2, let's say. The way you would do such a limit is you just try to plug the number into the formula there. That's always how you should approach one of these limits. You just try to plug the 1 in. You get 1 squared plus 2 times 1 minus 3 over 1 squared minus 3 times 1 plus 2. This is 1 plus 2 minus 3 over 1 minus 3 plus 2. And that is 0 over 0. And I hope you remember, 0 over 0 does not cancel and equal 1. It also does not equal 0. It doesn't equal anything. It's not. It's nothing. It's called an indeterminate form. When you see 0 over 0, it does not mean the limit is 1 or 0 or does not exist or anything like that. It means nothing. You don't know anything about what the limit. It could be 0. It could be some other number. Whatever. How do you handle such a situation? Well, if you don't know L'Hopital's rule, you need to go back to the beginning of this problem and factor and try to cancel stuff. If you do know L'Hopital's rule, then you do L'Hopital's rule. So what it says is if you get 0 over 0, you can take the derivative on the top and the bottom. And you get, so this limit here becomes, you only do this if you get 0 over 0. In other cases, it will mess up the answer if you try and do this. But if you get 0 over 0, you can do L'Hopital's rule. What you get in this example is, so you're still taking the same limit as x approaches, you know, the same thing, but you're going to take the derivative on the top and the bottom. So on the top I get 2x plus 2. On the bottom I get 2x minus 3. And then I'm going to try to plug the values in again. So when I plug in 1, I get 2 times 1 plus 2 over 2 times 1 minus 3. And that is 4 over negative 1. Negative 4 is the answer. All right, so this is a typical usage of L'Hopital's rule. Like I said, in this particular problem, it's possible to do without L'Hopital's rule by going back and factoring. But we are talking about L'Hopital's rule. All right. Sometimes you need L'Hopital's rule, and we're going to do examples later on today in which you definitely need to do L'Hopital's rule. All right. I think this is where we sort of ended up at the end of talking about this last time around. Here, I'm going to say something a little new, something that wasn't that I didn't mention last time. You can do the same L'Hopital rule trick. By the same trick, I mean take the derivative on the top and on the bottom. Same trick works if we get something like infinity over infinity after plugging in. All right. So this example here is an indeterminate form of type 0 over 0. That's what the book says. This is an indeterminate form of type 0 over 0. If you plug in and you get infinity over infinity, you can also use L'Hopital's rule in that case. So, for example, if I'm doing limit as x goes to infinity of e to the x over x, right? You have to think about what will happen in this fraction if the x becomes very, very large. And the answer is, well, if the x goes like to infinity, e to the x also is very large, and x also is very large. So basically, both the top and the bottom are becoming very, very large. So this, when I try to plug in, this is like, I mean, we don't typically write things like this because these are not real numbers, but you basically get e to the infinity over infinity. E to the infinity is sort of like infinity. What I mean by that is if the exponent in e to the x is super big, then the value of that whole thing is also super big, right? So this is a sort of maybe I'll put this in a blue bracket to mean like this. What I wrote there is not actually very formally meaningful. There's no such thing as e to the infinity, and you can't use infinity in a fraction like that as if it were a real number. But I hope that you know what I mean. What I mean is as x becomes infinite, you're going to get something that's very, very large in the denominator here. And the numerator is also very large. So what is infinity divided by infinity? This is like something that they, do they talk about this on the playground? I don't know. This is like a stoner topic of conversation. You sit around with your bros and talk about what infinity divided by infinity is. The answer is that's nothing. Like it doesn't cancel out and give you 1. It's just like 0 over 0. It doesn't actually tell you what the limit is. It is an indeterminate form, and we can use L'Hopital's rule in this case also. So we can do L'Hopital's rule. What you get is you take the derivative on the top and the bottom. You're still going to do the same limit. Limit as x goes to infinity. I take the derivative on the top and the bottom. What do we get? The derivative of e to the x on the top is e to the x. The derivative of the x on the bottom is 1. So this is actually just lim x goes to infinity of e to the x. And that is infinity, right? As the exponent gets very large here, e to the x itself also gets very large. So this is infinity. The end, all right? That's the value of the limit. It means that e to the x gets really big, and even if you divide e to the x divided by x, it still gets really big when the x is becoming very large. All right. I'm going to try and summarize this L'Hopital's rule and write it as like this is the official statement of L'Hopital's rule as a theorem. The official description of what L'Hopital's rule says. It says this: if f and g are two functions and they are differentiable, remember that means just like they have a derivative. You can take the derivative of f and g. And remember, L'Hopital's rule is about what happens if you try to plug in on the top and the bottom and you get 0 divided by 0. So eventually, can I leave a little blank spot? What I'm eventually going to talk about is this, the limit of f of x divided by g of x, right? So you think of f as being the numerator and g as being the denominator. So if f and g both have derivatives, and when you try to plug in on the top, you get 0. And when you try to plug in on the bottom, you get 0. That's what I'm saying right here. If you get 0 on the top and also get 0 on the bottom, or if you get infinity both times, or Lim X goes to a of f of x equals plus or minus infinity. I mean, it could be positive infinity or negative infinity. Either way, you can use L'Hopital's rule. And Lim X goes to a g of x equals positive or negative infinity. So all of that is saying when I try to plug the number in, either you get 0 over 0 or you get infinity over infinity. Then here's the conclusion. Then this limit is equal to the limit of the derivatives, f prime of x divided by g prime of x. All right. This is the L'Hopital's rule formula. It only works in the scenario that I described above, right? If it only works when you get 0 over 0 or infinity over infinity when you plug the values in. All right. I want to talk about why this is true. This L'Hopital's rule has always seemed sort of mystical to me. It's so weird that you do that. Take the derivative on the top and on the bottom. I consider that to be very weird because I have great respect for the quotient rule, right? When I see somebody looking at a fraction and taking the derivative on the top and the bottom, it makes me nervous because you're not supposed to handle fractions like that with derivatives, all right? If you want to take the derivative of the whole fraction, you do the quotient rule. You don't do this derivative on the top and derivative on the bottom. But it turns out in this particular scenario, derivative on the top and the derivative on the bottom actually is useful for something. It's strange. Why should you believe that the limit of f divided by g is equal to the limit of f prime divided by g prime? I want to talk about a very special case. So this is actually easy to see why. Not in general, but in some special situations, it's easy to see why. If f of a equals 0 and g of a equals 0. So if it happens that you can actually plug the value directly into these formulas and you actually get 0 over 0, actually this is the typical situation here. This is slightly different from what I set up here, which was that the limit is 0 and the limit here is 0. So what I'm saying here is not only is the limit 0, but actually the value at those particular points is 0. In this case, then actually you can see without too much trouble why the L'Hopital's rule formula. So in this case, what do you actually get if you do Lim X goes to a of the derivatives f prime of x minus g prime of x? What is that? In this case, you can write the definition of the derivative here. What it's going to look like is this now. This, of course, we typically don't use the definition of the derivative, but if you want to, you can. Remember, this is the definition of the derivative. You've probably seen one form where it's like f of x plus h, and the limit as h goes to 0, but this is the other form of the definition of the derivative. That's the derivative of f on the top, and then the derivative of g on the bottom. Looks like this. All right. We can simplify. This is a big fraction on fraction here. How can you simplify that? Anyone want to tell me? Shout it out.
We have a common denominator, so we can do something with those, correct?
They have a common denominator?
Yeah, we can rework that x minus a, correct?
Yes. Actually, they have these things. I don't know how you like to do fractions on fractions. I heard some kids on the playground say, you do keep, change, flip. I don't really know what that means, but if anybody heard that before? It's like if you have something like A divided by B over C divided by B. This is sort of the scenario that I'm looking at here. What does that simplify to?
That would just be A over B, correct?
It's just A over C. I think that's what you meant. The B denominators cancel each other out. Yeah. So if you want to write this in steps, you could write it this way: A over B times B over C. Rather than dividing by the fraction, you multiply by its reciprocal, and then the b's cancel. You get A over C. Anyway, what do you get in our case downstairs here? Those x minus a's will just cancel in this fraction. And what you're left with is lim of f of x minus f of a over g of x minus g of a. I like this. And remember, the whole scenario here is that when you try to plug in on the top and the bottom, you get 0 both times. That is to say, what I said here, f of a is actually 0, because when you plug in the a, you're supposed to get 0. And g of a is also 0. So this actually is equal to lim x goes to a, f of a over g of a. And that's f of x, sorry, over g of x. And that is the L'Hopital's rule, right? This equals that. So this is sort of why it's true. I mean, I don't have a real intuitive reason, like if you were explaining this to a 7-year-old, how you could convince them, but it's because when you do the derivative, a whole bunch of stuff is going to cancel out, and you end up getting the same stuff, right? That x minus a part cancels. All right, so this is why the L'Hopital's rule is true. It's because a bunch of stuff cancels in the case when you have 0 over 0. All right, the same kind of thing happens when it's infinity over infinity, although that's I don't want to get into the details of that. All right, I want to just do a bunch of examples, and then I have some for you all to try. Let's try a bunch of examples. How about you know, these all kind of go similarly, although there are some little ins and outs, as you'll see. Lim as x goes to 1, ln x over x minus 1. What's it going to be? Well, we should, as always, begin by trying to plug the number in. If you get 0 over 0, then you can use L'Hopital's rule. If you don't, then actually you can just stop. If you don't get 0 over 0, you get some number, then that number is the answer of the limit. So you should always try to plug in first. Anybody recall what's the ln of 1? On the bottom I can say I'm going to get 1 minus 1. What's ln of 1?
No.
It is 0. Yeah, this is a true fact about the natural log. So this is 0 over 0. That means I can use L'Hopital's rule. So this, I do the L'Hopital's rule, and I get the derivative. So it's lim again, x goes to 1, and we take the derivative on the top and the bottom. Anyone recall what's the derivative on the top going to be?
1 over x.
1 over x, excellent. And on the bottom, the derivative is show me the fingers if you want. Just 1, isn't it? X, the derivative of x is 1, and that minus 1 goes away. So let's just, you know, I intend to now plug the limit in, but I can simplify it. 1 over x divided by 1, that's just 1 over x, right? And now I can plug in to take the limit. Plug the 1 in, I get 1 over 1, which is 1. There you go. So the limit is 1. This is a simple, classic L'Hopital's rule. All right. How about another? How about this? Lim x goes to 0 of cosine x minus 1 over x. All right. This one is very similar. We should, as always, try to plug the value in. Plug in 0, you get cosine 0 minus 1 over 0. Cosine of 0 is 1, so up top I get 1 minus 1. And this is going to be 0 over 0, which means I can use L'Hopital's rule. So I go back, I plug it in, I get the derivative, well, lim again, x goes to 0. Take the derivative on the top, cosine becomes negative sine x. Hope you remember that one. Minus 1 will go away on top because I take the derivative, it goes away. And then divided by the x becomes a 1. That's the L'Hopital's rule step. And then I try again to plug in. I get negative sine 0 divided by 1. That's 0 over 1. Huh? 0 over 1, which is 0. So in this case, the answer really is 0. Sometimes when you see 0 over 0, you actually are going to end up with 0, but there's no way of knowing without doing it. All right. All right, I got a couple more. How about slight variation? Cosine x minus 1 divided by root x. How about that? Very similar. So again, we're going to begin by plugging in the 0, right? This will become, again, cosine 0 minus 1 divided by, this time, square root 0 on the bottom, but that doesn't matter. You're going to get 0 over 0 again. The top cosine of 0 is still 1. So you still get 0 over 0. All right. The L'Hopital's rule is going to be a little more complicated because the derivative, on the bottom is more complicated, right? So I get lim x goes to 0 again. Up top, take the derivative just like before. It's going to be minus sine of x. On the bottom, what's the derivative of square root x?
X to the 3x.
Yes, she said 1/2 x to the minus 1/2, right? X to the 1/2 is what it starts as, and then you decrease the power by 1, so you get x to the minus 1/2. Okay. This is looking a little complicated. I would say, I intend to take the limit by plugging in 0 again, but let's rewrite this, try and simplify that thing because it's a little weird as written. First of all, 1/2 in the denominator will just turn into a 2. And would you mind if I put, well, still got to put this limit here. Negative 2, the negative comes from the numerator, and then the 1/2 in the denominator will flip up and become a 2. And then I have sine x. X to the negative 1/2 in a denominator, I can just write as x to the 1/2 in the numerator. So actually there's no need for the fraction anymore. All right. Negative power means it goes in the denominator, but if there's a negative power already in a denominator, that's the same as putting it up top. All right. And now we can plug in x equals 0. What do we get? Negative 2 sine of 0 times 0 to the 1/2. And that's just negative 2 times 0, right? Sine of 0 is 0, and 0 to the 1/2, that means square root of 0, which is 0. So 0 is the answer. All right. So this is slight variation, right? I took this example, which had just x, changed it to square root of x, and the answer ended up being the same. So putting a square root of x down there makes no difference in this particular problem. All right. Any questions about that one? So sometimes it gets weird and you got to sort of simplify it in the middle. That was an example of that type. Okay, how about the more sort of traditional example is just when we're looking at polynomials like this. How about x squared minus 3x plus 2 over x squared plus 2x plus 1? All right. Limit as x goes to 2. We should, as always, try to plug the value in and see what happens. So plug the value in here. I get 2 squared minus 3 times 2 plus 2 over 2 squared plus 2 times 2 plus 1. What do you get? 4 minus 6 plus 2 over 4 plus 4 plus 1. Actually, this is not 0 on the bottom. It's 5. And it's 0 on the top. Okay, so this one, I threw this in there just to sort of trick you. This is not a L'Hopital rule problem because I didn't get 0 over 0. Anybody want to suggest, what do we do then? If you, what if you don't get 0 over 0? What are you supposed to do then? You cannot use L'Hopital's rule.
Once you if you don't get 0 over 0 for plugging in, doesn't that give you your answer for what the limit actually is equal to?
Yeah, right. The answer is like if you don't get 0 over 0, that's actually better. That means you're done. So when you see this, what does that mean? The limit equals
0.
0.
yeah, it equals 0 divided by 5, which equals 0. So the answer here is just 0. All right. You don't have to do L'Hopital's rule because you already know what the answer is. All right. The only case when you need L'Hopital's rule is when you get 0 over 0. What if just to refresh our memory, if we plug in and get something like, what if it was the other way around, 5 divided by 0? What does that mean about the limit?
Does not exist.
Yeah, then the limit does not exist. And so again, you can't use L'Hopital's rule, but you wouldn't want to because you're done at that point. You don't have to say anything else about the limit. You already know that the limit does not exist. All right. So L'Hopital's rule is only when you get 0 over 0. In all other cases, you don't even need it. You just say what the limit is immediately. All right, excellent. Whoa, I just threw my pen. Give me a moment. All right, sorry about that. Okay, I got 2 more examples that are a little more complicated. How about Lim X goes to 0. So this is another variation on this one that we just did. Remember we already did this one. Then we tried it again with the square root. We got 0 both times. How about this? With a cube. What's it going to be this time? Well, we do the same stuff, so you should try to plug in here. You get cosine 0 minus 1 divided by 0 cubed, and this is 0 over 0 because cosine 0 is 1. All right, just like before when we tried this. We are going to do the L'Hopital's rule. So you take the derivative on the top and the bottom. The derivative on top is minus sine x. The derivative on the bottom is 3x squared. All right. Now, in the previous example, I was able to simplify things, but really this one doesn't simplify at all. We should just try to plug the value in, and we get negative sine 0 divided by 3 times 0 squared. This is, again, 0 over 0. What are we supposed to do now? Anybody have a suggestion? This hasn't happened in our other examples.
We derive again?
Yeah, do it again. This is the old squeeze gats till my clips is empty situation. If you do the L'Hopital's rule once and you still get 0 over 0, well, you can just do L'Hopital's rule again as often as you need to until you don't get 0 over 0 anymore. So let's take the derivative again. On the top and the bottom. And, hopefully you won't just keep on doing this forever. You get, okay, so from here, negative sine x on the top becomes negative cosine x. And on the bottom, 3x squared becomes 6x. And now I plug in again, and I get minus cosine of 0 divided by 6 times 0. Actually, this is not 0 over 0. This is minus 1 over 0, which means the limit does not exist. DNE is what I write for does not exist. All right. That's how it's done. Any thoughts about this? This is the old do it again situation. It happens sometimes. I got one more example. And then I have some for you all to try. Oh no. I will eventually, but not immediately. How about Lim X goes to 0, tan x minus x divided by x cubed. All right. So, like before, I'm going to try to plug in here. I get tan 0 minus 0 over 0 cubed. Tan 0 is 0, so this is 0 over 0. So we can do L'Hopital's rule. It becomes Lim X goes to 0. On the bottom, it's going to be 3x squared. Anybody remember the derivative of tan? slightly more obscure one?
Like secant squared of x.
Yeah, it's secant squared of x. And then minus 1. He almost said sex. It's secant squared of x. All right, and then we're going to try to plug in. Remember, secant means 1 over cosine, right? So when it comes to plugging in here, that's how you should think of secant squared. We're going to plug in. We get plug in 0. So it's 1 over cosine of 0 squared. That's the secant squared, right? Secant is 1 over cosine. And then minus 1 over 3 times 0 squared. But of course, we have said several times cosine of 0 is 1. So this is really 1 minus 1 over 0. 0 over 0. All right? So we got to take the, we are going to do L'Hopital's rule again. And now, unfortunately, L'Hopital's rule is going to get a little more complicated because we have this, I mean, I have to take the derivative of secant squared, which is kind of a pain. But we can handle it. On the bottom, we have 3x squared, right? And on the top, we have secant of x, the whole thing squared. And I happen to remember, anybody actually remember this one? I know some of you are good formula memorizers. Anybody remember this one? I would not expect you to. It's this, secant x times tan x. I don't typically have these more obscure ones memorized either. But anyway, I have up top the derivative of secant squared. We're going to do the chain rule on secant squared. And so it becomes 2 times secant x to the 1. I'm doing the chain rule with the square outside of secant. And then times the derivative of secant, which is all of that stuff over there. Secant x tan x. All right. So this is an example where things can get a little nasty, but hopefully it'll work out eventually.
Why wouldn't the derivative on the bottom be 6x?
6x, yeah. I don't know why. Sorry. Thank you. 6x.
Yeah.
Yeah. 6x is correct. I forgot to take the derivative on the bottom. All right. Okay, we're going to try to plug this in, right? That's what we always do. Can I just rewrite this, first of all, just to, I suppose, simplify a little bit? The 2 and the 6 can kind of make a 1/3 out front, and then what I have here is secant squared x times tan x on top over x, right? I just combined the 2 secants, and I pulled out the constants. This doesn't really matter, but anyway, I'm going to try to plug the value in again. We get 1/3 out front, and then times secant squared of 0 tan 0 over 0. Secant squared of 0, remember secant of 0 is 1 because secant is 1 over cosine. 1 over cosine of 0 is 1. So this is actually 1/3 times 1 times 0 over 0. We again get 0 over 0. And so we must again do L'Hopital's rule. And it's at this point when you start to wonder about, like, is this ever going to get any better, or am I just going to be doing the same nonsense over and over again? Actually, I mean, it's good to wonder, but actually in the next step we're going to actually get an answer. So this will not go on forever. Before taking the derivative, actually, would you mind if I wrote this? Maybe I should have done this before. Instead of secants and tangents, can we just write everything in terms of sines and cosines? It's a little nicer. We have cosines, secant is 1 over cosine, and tan is sine over cosine. I think this all amounts to sine x divided by cosine. Sorry, there's an x in the denominator. All of that. I believe this is what you get when you write everything in terms of sines and cosines. It's a cosine cube on the bottom because I get 2 cosines from the secant squared plus another cosine from the tan. All right. And now from this, I'm going to do L'Hopital's rule one final time it turns out, I mean, you have no idea if this is really gonna go on forever or not, but just because I know this is the last time you have to do it. I'm gonna do the quotient rule here, which is gonna be a big nasty thing. Sorry, we need to keep the lim here. I'll just start a new line. I'm going to do the quotient rule. So it's going to be the bottom thing. What? Sorry, I'm going crazy here. I'm not doing the quotient rule. I'm doing the L'Hopital's rule instead. We take the derivative on the top and also take the derivative on the bottom. This is easier than the quotient rule. The derivative on the top becomes cosine x. The derivative on the bottom becomes, I have to do the product rule now, right? I have x times the cosine cubed. So I do the first thing like it is, x times the derivative of cosine cubed is 3 cosine x squared times sine, negative sine x. All right, that was the chain rule on the cosine cubed. And then plus, continuing the product rule here, the second part, cosine cubed x times 1. All right. I think I did that right. And then I'm going to plug the value in. And this time we're not going to get 0 over 0. So plug in. What do we get? 1/3 out front. Cosine of 0 on top, which is going to be 1. And then on the bottom, I get 0 times 3 times 1 squared times negative 0 plus 1 cubed times 1. All right. When you plug in 0, the cosines become 1, the sines become 0. And all of this ends up being, I got 1/3 out front, 1 over this the whole first part here is 0. This is 1. So this is 1. The answer is 1/3. After all that, we get 1/3. So this is like the most complicated example that you would ever be called upon to do here. I had to do the L'Hopital's rule 3 times, and involving lots of weird trigonometry derivative formulas. All right, this is like the hardest L'Hopital's rule problem you are ever likely to encounter. And on our tests or whatever, I would not expect you to remember the derivative of secant, although I suppose it's not so hard to figure that out. All right, any questions about that one? Excellent. Okay, I got one more thing to say before I let you guys try some, and that is some variations on L'Hopital's rule. So we've discussed indeterminate forms, indeterminate forms of the type 0 over 0 and infinity over infinity. There are others though. So there are other scenarios in which when you try to plug into a limit, you get something that doesn't make any sense and you can handle it using L'Hopital's rule. So others are things like, remember the reason these are indeterminate forms is because, for instance, infinity over infinity, you're basically asking yourself, what am I going to get when I divide one very large number divided by some other very large number? And the answer is, well, you can't really predict what you're going to get. You might get 1, but you might also get 0 or something else that you can't tell just by looking. Another question that you could ask yourself, and these are more sort of stoner type questions, what about 0 times infinity? You got to feel like anything times 0 is 0, but also you got to feel like anything times infinity should be infinity. So what are you actually going to get when you multiply 0 times infinity? This too is an indeterminate form. So when you plug into a limit and it looks like 0 times infinity, you can't say what the answer is immediately. In fact, you can use L'Hopital's rule in this scenario. And the other would be, so this is a product, right? Product of infinity times 0. Of course, 0 times 0 is a perfectly fine product. It equals 0. Or infinity times infinity is also equal to like infinity. So you don't have to worry about those. It's just 0 times infinity. And then there's also an indeterminate form involving a difference of 2 infinities. This is indeterminate because, again, when you say infinity minus infinity, really what you have to think about is, what if I have one really, really big number and I subtract another really, really big number? What am I going to get for the answer? And the answer is, well, you can't say exactly. I mean, sometimes they might cancel out, sometimes they might not, right? This is an indeterminate form also in the form of a difference. We can use L'Hopital's rule in any of these situations. The problem is L'Hopital's rule, the formula for it, is only about quotients, right? F divided by G, and you take the derivative on the top and the bottom. There is no corresponding other formula that you use for these. The trick is, if you want to use L'Hopital's rule, we can use L'Hopital's rule here. You just force it into a quotient. So even if the thing you're looking at doesn't look like a quotient, you need to rearrange it yourself to make it look like a quotient. And we're going to do some examples of each of these two types, the product one and the difference. The product one is typically easy to do. You just redo it so that it's the division rather than multiplication. Let's try. I want to try one of each of those. How about this one? Limit x goes to 0 of x times ln absolute value x. Limit as x goes to 0. We should try to plug the value in first, like we always do. Of course, x is going to become 0 when I plug in x equals 0, and then I get times natural log absolute value 0. I suppose the absolute value maybe doesn't matter too much there. Actually, the absolute value kind of does matter. What is the natural log of 0? Well, if you look on a graph for the natural log, I hope you remember the graph of the natural log looks like this, right? And if I graph the natural log of the absolute value, it actually looks like this. It has both sides. This is the graph of natural log of absolute value x. And what are you going to get when you take the limit as x goes to 0? This goes down forever, right? So this value here is going to be 0 times, in fact, minus infinity, right? Minus infinity. And this is an indeterminate form. I get minus infinity because the graph of the natural log as x approaches 0 goes down forever, all right? And this we can use L'Hopital's rule. What you got to do is rewrite the original thing to make it look like a fraction. So I'm going to take this here, lim x goes to 0, x times natural log absolute value x. You rewrite it to make it look like a fraction. So I suppose there's two ways you could do this. I'm going to do it like this. I'll put the log up there and then divide it by 1 over x, all right? Ordinarily, you would never do this. This is making it sort of more complicated rather than less complicated. But the point of doing this is to force it into a quotient where now, when I try to plug in, I'd get infinity over infinity, right? Well, it's actually negative infinity up there. It doesn't matter about the signs, all right? Now, when you try to plug in x going to 0, you're going to get infinity over infinity, which means you can do L'Hopital's rule. So now I'm going to do L'Hopital's rule right here, right? I take the derivative on the top and on the bottom. So I get lim x goes to 0. Derivative of natural log x is 1 over x. And on the bottom, I have to take the derivative of 1 over x. Of course, 1 over x is x to the minus 1. And so the derivative of that is minus x to the minus 2. All right. And this is something that we should be able to rearrange those fractions. How could I rearrange this? It's 1 over x rather than a negative exponent in the bottom. That's the same really as negative x squared times 1 over x, isn't it? I just move the negative exponent inside of the denominator. You can move it up. What is that? just negative x, right? This is lim x goes to 0 minus x. You get 0. So the answer is 0. We started with a product of the form 0 times infinity, and you just shove it into a fraction, however it takes to make a fraction out of it by taking the reciprocal of something or other. All right, I got one more, and then I got some for you all to try. How about this one? Is especially weird looking. Limit as x goes to pi over 2 from the left. Tan x minus secant x. All right. Now these are slightly weird limits to do. I will refresh our memory just by looking at graphs of these things. You know, the first thing we're going to try to do is just plug in. What do you actually get when you take the limit of each part? The graph, I will refresh your memory, of tan x looks like this, where this is pi over 2, and so on, right? This is the graph of tan x. And then the graph of secant x looks like, and this one I had to look this one up myself. Well, I don't have this memorized, but the graph of secant x looks like this. It does this kind of thing. All right, where this is pi over 2. So when I try to plug in here, I get taking the limit as x goes to pi over 2 from the left. Actually, this from the left thing is important. It means I approach along this curve, and it goes up to infinity for tan. So the limit for the tan x is infinity minus, how about secant x? I approach pi over 2, but from this side, and again I get infinity. All right. So this is infinity minus infinity, and this means you can use L'Hopital's rule. Right? If I had gotten infinity minus negative infinity, actually that means infinity plus infinity, and the answer is infinity. So that's not a situation where you need L'Hopital's rule. It's only in infinity minus infinity. So we're going to do the L'Hopital's rule. Anyway, the suggestion to do L'Hopital's rule is you have to force it to look like a fraction. Anybody got a suggestion? How could we force this to look like a fraction, a single fraction?
Well, we said earlier we can make secant into 1 over cosine.
Yes.
Tangent into sine over cosine.
Yeah, this is a great idea. So what I'm looking at is tan x minus secant x, but this is sine x over cosine x minus 1 over cosine x. Okay. Now I want really one single fraction. Can we make this into one single fraction?
Yes, we can. We can represent it as sine x minus 1 over cosine x.
Excellent. Yeah. These are two fractions with a common denominator, so you can just add them together by adding the numerators. It's subtraction in this case, and then keep the same denominator. Great. So this is often hard to do. There's no standard way to force a difference of two things into a fraction, but usually you're going to try to write them using a common denominator and then add them together into a single fraction. Okay, that's what we're going to do though. So what I want then is lim x goes to pi over 2 from the left. Now probably the left versus right is not going to be relevant anymore, but it's this, right? This is my transformed version in terms of writing everything as a fraction. Okay, now this one, just to be sure, what happens when you try to plug in? I get sine pi over 2 minus 1 over cosine pi over 2. And sine pi over 2 is 1, so this is 1 minus 1 over cosine pi over 2 is 0. So this is 0 over 0, which is good. This sort of makes me feel good about using L'Hopital's rule now, right? I force it into a fraction in which I get 0 over 0, which means I should use the L'Hopital's rule like we always do. X goes to pi over 2 from the left. The from the left really didn't matter when I plugged it in, and it's not going to matter in the next steps either. Take the derivative on top and the bottom. We get cosine x on top, negative sine x on the bottom. Plugging in again gives me cosine pi over 2 divided by negative sine pi over 2 This is 0 over negative 1, and the answer is 0. That's
Professor,
how
could
we...
you also just say that's negative cotangent?
Yeah. Yes, if you want to. Do you know what cotangent of pi over 2 is? I don't have that.
Personally, I do not.
Yeah,
But
so
I think it just looks cleaner.
Okay, yeah. I mean, because I intend to plug this value in, I find it easier to write this way, just because I know what cosine of pi over 2 is, and sine of pi over 2, but I don't know what cotangent of pi over 2 is. But however you want to say is fine.
Sounds good. I know that on certain assignments you don't necessarily require us to write it all the way out. And so for that, I would probably write it as negative cotangent of pi over 2. But because you wanted us, for L'Hospital's rule, you want us to like simplify it out, it's probably easier to represent it as you have it.
Yes. So I would be dissatisfied if you just said the answer is cotangent pi over 2, or negative, and said like that's my answer, because this can be a little misleading. I mean, that equals 0, and so this is not incorrect, but if you were going to go there, you might as well have just started at the very beginning and said the answer is tan pi over 2 minus secant pi over 2, and just said that's the answer. Whatever that is, that's the answer. But actually, this is a bogus answer because both of these do not exist. And what's the guarantee that this even exists at all? I mean, in fact, it does exist and it equals 0. But yeah. Anyway, all that to say, it can be a little misleading to just leave answers when you're dealing with the weird trig functions, which have asymptotes. I would tell you, on a test or something, I would be clear about how I wanted you to write the answer. All right.
Okay, thank you.
We got about 10 minutes left. I got some for you guys to try. I don't know if you can do all of these in 10 minutes. Probably not. But we'll do some of them at least. These are all, so most of these are easier than, these ones that I've been doing at the end here. See what you think. All right, I'll give us a few minutes and then we can talk about these. All right, we got about 5 more minutes till we're done, so let's go over these. I don't know if you made it through all of these. It's fine if you didn't. The first few are pretty straightforward. So this one here, you should have tried to plug in. You get 0 over 0, which means you can do the L'Hopital's rule, and you should get 2x over 1 for the derivatives. Still doing lim x goes to 2, and then this becomes 4, right? When you plug in x equals 2, you get 4. I hope everybody got that one. Any questions about that one? I hope that's what you said. Okay, the next one here, cosine x over sine x minus 1. Again, when you plug in, you should get cosine pi over 2, which is 0, over sine pi over 2 is 1, so you get 0 over 1 minus 1 here when you plug those in. So you should do L'Hopital's rule. You get minus sine x divided by cosine x, like that. Lim x goes to pi over 2. And then what are those? Sine of pi over 2 is 0, and cosine of pi over 2 is 1. So the answer here is 0. Anybody agree? I hope that's what you got.
Professor, I did the same thing that I did with the cotangent on the last one, but I did it with the tangent on this one, and the tangent of pi over 2 is a little bit easier to remember than that of the cotangent.
Okay, yeah, so tan of pi over 2 is 0. Is that what you said?
Don't forget that negative, obviously, but because it's 0, that doesn't really matter.
Right. But something's weird about that. Because tan of... I did this wrong, sorry. Did anybody totally disagree? Tan of pi over 2 does not exist. That's an asymptote. Yeah, this because sine of pi over 2 is 0. Sorry, I had this upside down. Cosine of pi over 2 is 1. Is that right? No, I wrote it backwards again. It's this. It's 1 over 0. Right? Sine goes like this, where this is pi over 2. And cosine goes, you know, the way cosine goes. So, yeah, the answer here is DNE. Or you could have said tan of pi over 2 does not exist because that's where tan has an asymptote on the graph. Sorry about that. This is the correct answer, is a DNE. Okay, I said those were the easy ones, but I messed that one up. Let's try these ones here. This one here, you get, when you try to plug in, you get infinity over infinity because you have a bunch of stuff added together, which are all going to be infinite. You do the L'Hopital's rule, and it becomes limit of 6x over 2x plus 5. You try to plug this in, and again, you get infinity over infinity. So you do L'Hopital's rule again. This time you just get 6 over 2, which is 3. So the answer for that one is 3. Probably in your calculus class, you also learned there was a trick when you have these guys, ratio of polynomials. You can look at the degrees on the top and on the bottom, and if the degrees are the same, you get the ratio of the coefficients of those terms, which in this example would be 3 over 1. So you get 3 either way, but that's doing with L'Hopital's rule. Okay, cinch over sine. I hope you remember that cinch of 0 is 0 and sine of 0 is also 0. And so this, when you try to plug in, you get 0 over 0. When you do the L'Hopital to that, the derivative of cinch is cosh. The derivative of sine is cosine. And then when you plug in this time, you get 1 over 1. So the answer for that one should have been 1. Because cosh of 0 is 1 and cosine of 0 is 1. Okay, what about this one here? These last two are a little more interesting. Maybe we'll just start off next time with that very last one, but we can talk about this one. When I try to plug in infinity here, it looks like sort of infinity times e to the minus infinity. How do you interpret e to the minus infinity?
It's an exponentially growing function of 1 over e.
Yes. Yeah. That to me is still kind of confusing. This I would think of as like this, right? 1 over e to the infinity, and that would be that's basically 0, right? Because 1 over something infinite is going to look like a 0. All right. So this is something which, when you try to plug in, it looks like infinity times 0, which is that indeterminate form, you know, of type 0 times infinity, or infinity times 0. And so we want to rewrite this to make it look like a fraction. Anybody got a suggestion? How can I rewrite this so that it looks like a fraction? How about, since it's time to go, I'll just say, how about x over e to the x, right? I already see a negative exponent there, so you might as well write that as a denominator if you want to force this to look like a fraction, x over e to the x. If I were to plug in here, I get infinity over infinity, which means I can do L'Hopital's rule, and I get Lim X goes to infinity 1 over e to the x, because the derivative of x is 1, derivative of e to the x is e to the x. And then when I plug this in, we get 1 over infinity. This is 0, right? So the limit equals 0 in this example. All right, and I think that'll have to do it. Sorry to leave you at the last moment here. Let's just do this one real quick at the beginning next time, and then we'll go on to something completely different. All right, I will see you all in person tomorrow. Have a good one.
Well, thank you, Professor. Take care.
Thank
Have a
you.
good rest of your day.
Yeah.
Bye-bye.